right, good afternoon, everybody, and welcome. This is Microsoft SQL Server Management Basics for non-DBAs. My name is Denny Cherry. My email address and my contact info. Quick bit of housekeeping real fast. Please do remember to make sure your cell phones are muted. In this giant room, they will echo like there's no tomorrow if you let them ring. So like I said, my name is Denny Cherry. Email address is up there as well. I am a Microsoft Certified Master for SQL Server 2008. I am a Microsoft MVP for the SQL Server product, among various other things. I've got business cards up here if you want to grab one to grab my contact info. So I've broken today's presentation down into kind of these 8 sections that we're going to talk about. Files and file groups and disks, backups, recovery model, database maintenance, compression, database corruption, compatibility levels, and then indexes. So before I get started, where are my developers at? Okay, huge number of you, awesome. Systems admins, people who think this is the line for the Surface. Few people, okay, cool. So by the way, thank you all for coming to the session instead of standing in the line. I know it's a lot shorter right now than it was 2 days ago, but it is still like a 2-hour line, so don't go anywhere. So the first thing we talk about is files, file groups, and disks. So we're going to start with file groups. File groups are logical constructs within the database, and on our file groups, or within our file groups, we put the actual files. These files are going to be the physical files that we see on disk that contain the data. The reason we have file groups is so that we can spread tables across multiple hard drives, or across multiple disks within SQL Server. The reason we want to do this is because back when SQL Server was created, it was called Sybase, and hard drives were not very large. So we needed a way to put large objects across multiple sets of disks without having, these ridiculously large disks that we really couldn't get back then. Today we still do this because our table objects are now even bigger than they were before. I've got clients that have 1 terabyte tables. And I obviously don't like having giant 1 terabyte LUNs sitting around because they're really hard to manage and hard to move around the storage array. So we create smaller disks, we put 1 file on each disk, and we bundle these files up into a file group. So when we create an object, we create that object on the file group, and then SQL Server is going to spread that file, or rather that table, across all the files within that file group. SQL Server is going to use something called proportional fill to try to balance the amount of data within the files in that file group. It's going to try and do its best to keep the amount of free space within all those various files as even as possible. So this is one of the reasons you'll see a lot of recommendations out there that say to, when you create multiple files, set them all to be the same size and set the auto-growth settings for all of those files to be exactly the same. You'll also see this causing problems if you add a new file into a pre-existing file group, because SQL Server is basically going to hotspot that file until that file sort of fills up and it gets to about the same size as all the other files. There's not really anything you can do about that, but it's something to keep in mind if you do have to add files to grow your database. So obviously disks hold files within the database, and we can lay them out realistically just about however we want. The typical recommendation is put your data files on RAID 5 or RAID 10, your transaction logs on another RAID 10 array, and your tempDB on yet another RAID 10 array. The reason we want all this stuff spread out is because we want to minimize the contention between all these disks. Typically, our data files are going to be reading a lot of data. Our transaction logs are going to be basically just almost always writing data, and our tempDB database is going to be doing both. And we need to minimize the amount of contention across all these files while all this is happening so we get the best throughput we can possible. This is specifically true of the transaction log. As SQL Server is going about doing its thing, if the transaction log can't write data to the disk that it's sitting on, SQL Server is not going to be able to continue forward with that transaction. Within SQL Server, everything must be written to the transaction log before it can actually be committed to the actual data files later on. And that's all done asynchronously. So the fastest bit of writing you need to be able to do is to your transaction logs disk, because that's where everything has to go before the user is going to get a response back that says that insert or that update or that delete was successful. When we set up our databases, every database is going to have at least two files. The first file is going to be the master data file, or the MDF. The second file is going to be the transaction log. If you query from sys.sys databases, or sorry, sys.sys database files, you'll always see that file number 1 is your main data file, file 2 is your transaction log file. You can add in basically as many additional database files as you need to grow the database and size the database however you need. You can have one file group, you can have multiple file groups, all depending on how you want to lay things out on the disk and how you want to isolate things from other pieces of the database. The kind of database you're building is going to determine what sort of methodology you want to take when it comes to actually building your data files and laying them out. For example, in a traditional OLTP database, we're probably just going to throw everything into one file group because we just want all the data to just have the fastest possible disk access time. Because all we're doing is a lot of little onesie, twosie writes. So we don't have huge writes happening all at once and then moving of data from one place to another. Now, on the flip side of that, if you're building a data warehouse, then you're probably going to have multiple file groups laid out because you're going to have a staging file group and a production file group so that you can bulk load all your data into the staging file group and then do whatever manipulation needs to be done there and then move that data into your production file group. So we want those on separate disks, and doing that requires separate file groups because as we're reading from one drive and writing to another, we don't want any contention between those drives. So we need to make that data move as fast as possible. So backups. Backups are the most important thing you should be doing to your SQL Server database. Having a database online and is operational is great. But if I go in and delete data, or if my database becomes corrupt and I don't have a backup, I have no way to rebuild my system, no way to keep my business running. Many cases of companies actually going out of business just because they don't have a good backup policy in place. In SQL Server, we've got 3 different kinds of backups. We have full backups, we have differential backups, and we have transaction log backups. We do not have incremental backups, which you may see on the Windows Server side. And we have the ability to do snapshot-based backups if you're in like an EMC or a NetApp sort of storage array environment. Those are separate and very different from normal traditional SQL Server-based backups. Now, keep in mind, when setting up backups, if you're running in a virtual machine and you're taking snapshot-based backups from some sort of host-based backup provider like Veeam or some sort of other VSS-enabled provider, technically those are unsupported backups. If you have a problem and you need to restore from those backups and can't, Microsoft does not have to help you. So keep that in mind. Even though they're working, that they may not be supported if there is a problem. So the full backups, there's some advanced backup options I'm not really going to go into here. The first one being advanced, the file group backups. This is where we can actually take a backup of just part of the database at any one time. This is typically used for data warehouses to minimize the amount of time it takes to do the backup, maybe by only backing up this year's information instead of backing up the entire database. Always make sure that you're writing your backups to some other machine. We don't want to save the backups on the local server, because if the local server fails, and that's where the data files are and the backups are, we've just lost everything that we have, including our backups. The same goes for if you're storing your data on a SAN. If you're working in a large enterprise and you've got LUNs presented off a SAN and you're running your production database off that, don't write your backups to that same LUN, or preferably not even the same SAN, because you don't want everything sitting in one place. Because again, if you lose the data, you lose the disk, you've just lost everything. So full backups. Full backups are a point-in-time copy of the database as of the state the database looked at when the backup completed, not when the backup started. It's a common misconception. As the backup's running, once it's copied all the data off the disk, it will then take all the dirty pages that are in memory that have been changed during the process of the backup happening, and it will write those to the backup as well as any transactions that are in flight, and those are all going to get copied to the backup as well. Once the backup's finished, all that data is released and flushed down to the disk, but the backup itself will look exactly like the database looked when that backup was completed. You should be running your full backups either daily or weekly. depending on what recovery model you're in and what your recovery policy is going to look like and how long it's going to take you to restore this data. For large databases, 100 gig, 200 gig, multi-terabyte, et cetera, you're probably going to do daily full backups and then do your transaction log backups over time as you continue to move on. So the second kind of backups, which apparently I don't have slides for, was the differentials. So differentials are going to take a copy of all the data that's changed since the last full backup occurred. So if you're a sysadmin and you're used to incrementals, where you simply take all the changes from the last fuller incremental, these are different. So this is from the time of the last full backup. So if all you do is take a full backup on Monday and take a differential every day, your differential is going to get bigger and bigger and bigger every day because it includes all the changes from the prior one. Now the upside to this is when we're doing our restore, all we restore is the full and then the most recent differential. We don't need to do every differential. So the third backup type was the transaction log backup. Now this is only going to be available in 2 of the recovery models, bulk logged and full, and I'm going to talk about those in a couple of minutes. Transaction log backups are actually taking the data out of the transaction log and actually moving it off the disk somewhere else. This gives us the ability to do point-in-time restores and get back to very, very specific points in time. I can tell a database to restore to within 1 millisecond of where I want it. If I don't like where the database has been restored to, I can roll it forward to the next second or the next millisecond. I can have very, very fine-grained control. If I'm using what's called named transactions, I can actually restore to a specific transaction within the transaction log. So say I'm going to do an upgrade. What I'll do is I'll create a transaction, name it, upgrade for 2013 May 5th. If I need to restore the database because the upgrade fails and things go horribly, horribly wrong, I can simply restore my full, roll all my transaction log backups forward, and simply tell the restore process, stop at this specific transaction, and it will stop at the end of that transaction. So I'll roll forward everything that happened and then just stop. So I don't need to know the exact time that transaction stopped. So this is fairly handy. So the next thing is recovery models. So like I said, there's 3 recovery models available in SQL Server. There's snapshot, there's bulk logged, and there's full. So these are the same 3 recovery models that we've had forever. This applies to every version of SQL Server from 4.2, the first version we had where we were separate from Sybase, all the way up to SQL 2014 that was announced, yesterday. The recovery model does a couple of things. The first thing it does is it controls the amount of logging that's happening to the transaction log. So in snapshot recovery model, we're still logging all our transactions, but we're simply not keeping that transaction log history in the transaction log, so we can't back it up. The way the snapshot recovery model works, do I have slides on it? Yeah, I do. So the way the snapshot recovery model works kind of at a high level is as the data is written in, when the checkpoint process happens, which flushes all the dirty pages to disk, all the pages that we've changed, all the rows we've modified, once those are all written to the actual data file, then the database is able to overwrite all the data within that transaction log file. With bulk logged and full recovery, the exact same process happens, but when the checkpoint is completed, SQL Server does not mark all those rows within the transaction log as being overwritable. I actually have to run a backup log command to actually back that data up and get it out of the database. The other thing that the recovery models do is they control the amount of recoverability that we have and how we're going to be able to recover this data and how fine-grained we're going to be able to get. With the snapshot recovery model, we're only going to be able to restore to that one point in time of that full backup or up to that differential. So that's all the fine-grained control we have. Whenever the backup was finished, that's the control we have because we're not doing any sort of transaction log backups. As it says up there, there's a minimal amount of logging that's happening with our snapshot recovery model. Now, it's not turning off logging. There's no way to do that in SQL Server. We are always logging all our writes. Every insert, update, and delete that comes into the system has to be logged for it to be changed in the database. So even though it looks like we're turning off transaction log logging with snapshot recovery model, we're actually not. What we're doing is, like I said, we're simply marking the transactions as being committed and hardened as soon as they're actually written to the actual data file. Once that's done, then we can overwrite those transactions. That helps us keep our transaction log file nice and small because we don't have to wait for this backup log operation to come through and back up all that data. Now, the snapshot recovery model does not give us, like I said, does not give us any point-in-time recovery at all. The bulk logged recovery model is kind of a funky recovery model because it's fully logging most of our operations. So our inserts, updates, and deletes, those are all going to be fully logged. But there are some minimally logged operations or bulk logged operations. Bulk logged operations are things like index rebuilds. If you're importing data through BCP or the bulk insert T-SQL command, or if you're using .NET and you're loading data with the bulk load process within .NET, those are all going to be bulk logged commands. What bulk logged commands are, or how they're logged, is we simply log the pages that the data is written to within the database. So within SQL Server, we don't just write rows to disk kind of wherever we want. All the rows are written to pages that are 8K in size. Those 8K pages are bundled up into 64K extents, so 8K pages. And that's how we write all our data. Those 8K pages are assigned to a specific object. When we're running bulk commands, we're not logging all the changes to the actual data on those pages. All we're logging is the fact that pages were allocated to an object. So for example, if I bulk load 1,000 rows into a table, I'm not going to get 1,000 records in my transaction log file saying there were 1,000 inserts. I'm going to get probably 3 or 4 rows in the transaction log that simply say that the 3 or 4 pages that those 1,000 rows fit on were allocated to that specific table. The fact that there's data on those pages is not logged, just the fact that the pages were allocated. All our other commands are fully logged. Now, we still have point-in-time recovery with the bulk logged recovery model to a degree. The problem with the bulk logged recovery model is that when we're writing all this bulk log data into the system, we're not logging all the actual row inserts. So if we need to back up the transaction log, we don't have all the data in the transaction log. So the way we get around this problem is when we do a transaction log backup and there's a bulk logged operation in that transaction log record, it simply backs up the entire 8K page that the data, or that was modified. So that's how we get the data into the transaction log backup, so we have a fully recoverable system. Now the problem here is that we don't have any sort of point-in-time notification about when this data was changed. So if we need to do point-in-time recovery, we cannot do point-in-time recovery to any time when a bulk operation is happening. So if we need to restore our database, we need to restore it to either before the bulk operation happened or after the bulk operation was completed. But we can't do it to any time in between while that bulk operation was running. So if you've got an application that's bulk loading data into SQL Server on a constant basis, the bulk logged recovery model is not going to be a very good option for you because you're not going to be able to actually restore to any sort of point-in-time recovery. So when you don't have the option of using bulk logged and you need point-in-time recovery, we have the full recovery model. In the full recovery model, almost nothing is going to be bulk logged. There's going to be a few things that are, but really not very much. The big thing that's going to be bulk logged for you is if you create a new table, an empty table, and you insert a huge number of rows into it, SQL Server will bulk log that operation for you because it doesn't need to log all those writes because it's coming from another table already. Basically, nothing else is going to be bulk logged. We have full point-in-time recovery, and we have full data protection because we can restore to any point in time, and we have every single piece of data that we ever had within the system. And we have another copy of it somewhere else, so we can recover the system to really any point that we actually need to. When we're restoring data, there's a few different ways that we can go about it. The goal when we're restoring data is to get the database into the exact state that it was in at whatever point of time that we pick. So the first thing we need to do whenever we restore data is do a full database restore. We need to take a full backup and restore it, because we have to have somewhere to start. Once we restore the full backup, an optional thing to do is restore a differential. Once the differential is done, or if we're not doing it, then we can do transaction log restores. And that will get all our data up to whatever point in time we want. Now, this process can take an incredibly long amount of time on really, really large databases. If I've got a 2 terabyte OLTP database that's getting tens of thousands of transactions per minute running through it, it's going to take a fairly long time for me to roll all those things forward, roll all those commands forward. So we actually have another option that we can use when it comes to restoring from databases that have become corrupt, where specific pages have become corrupt and we've lost specific data. And that's a page-level restore. Page-level restores allow us to literally pick a specific page within the database and restore that one specific page. We start by restoring that page from the full database backup, and then we roll through all our transaction log backups up to the current point in time. That brings that single page forward up until the current point in time where the rest of the database is at. This lets us take a terabyte database that's got one 8K page that's become corrupt and fix that one 8K page without having to write a terabyte of data back to the disk and then roll the transactions forward for the entire day. Because we only need to roll forward the specific transactions that touched that 8K page. When you're doing the page-level restore, SQL Server is smart enough to know which 8K pages you've just restored and which ones are out of sync with the rest of the system. So when it's rolling transactions forward, it only rolls forward the transactions that apply to that specific 8K page. The other option we have is to restore specific file groups. Click, there we go. So this goes along with the file group backups that I mentioned earlier. Again, fairly advanced option because we're restoring just individual pieces of the database. But this is typically done either for tables that are partitioned, where we need to bring back the system online with the current data right now, and we can restore the other data later, or with data warehouses where we've got bits and pieces of the tables that are kind of laid out all over the database. Now, people often ask me, what's the easiest way to get backups set up on a new SQL Server if I'm not familiar with getting backups set up? And honestly, the easiest way that I recommend to a lot of my smaller clients that don't have DBAs on staff is to use the maintenance plans in SQL Server. Maintenance plans get a fairly bad rap, and I fairly admit that, because they're not the most advanced things in the world, but they will get the job done. It's a nice graphical interface in Management Studio. You just drag whatever objects you want into the maintenance plan, save it, and schedule it, all right on one simple, easy screen. You're going to create a couple of different maintenance plans, one for your full backups, one for your transaction logs. If you don't want to go that route, there's lots of scripts out there that you can use. Ola Hannegren's got one of the better ones out there, you just run his stored procedure and schedule it as a SQL Server agent job. If you're a little more adventurous, you can set up scripts in T-SQL that will handle all these backups for you. You can also use PowerShell to back them up. It really doesn't matter what scripting language you use as long as the databases get backed up on a regular basis. Another incredibly important thing to do is to test your database backups. We never consider a database backup to be a valid backup unless we have actually restored that database backup to another machine. The same machine doesn't count because you may be protecting your database with some sort of encryption protocol, and we need to make sure that we can actually restore to another box to make sure that we can actually get back to all that data. So we want to restore those off to some other machine somewhere. Fortunately, you can script all this in T-SQL relatively easily and automate this entire process so that you don't have to go through manually doing all your backups and restores and testing everything. You can automate the entire process and just get emailed in the event that there's some sort of failure. So the next thing I want to talk about is database maintenance. Databases, just like your car, need a little bit of tender love and care to make sure that they are going to run at full efficiency. I see databases all the time that were set up years ago by the developer that built them and have never been touched again by anybody to do any sort of database maintenance on them. The biggest database maintenance that we need to do is some sort of index rebuilding or index defragmentation. Now, the net result, if you do either a rebuild or an index defrag, is exactly the same. So we only need to do one of these. But we need to make sure that we're doing some sort of index maintenance on a regular basis to fix any fragmentation that's in our database, or index fragmentation within our database. The reason for this is that fragmentation happens at a couple of different levels. The first thing that happens is the database gets spread out all over the database file. So this means that when SQL Server is trying to read that data, the head of the hard drive has to spin like crazy to try to get from one place to another to try to get all these database files or get all these database pages that it needs to get them into memory so that it can get the job that it needs to get done. The other thing we have to worry about is logical fragmentation within the database. This happens when what's called page splits occur. So when we build our indexes, if you're using just all the default settings, we have a setting called fill factor. What fill factor does is it tells the SQL Server how much white space to leave on the database page when it builds the index for the first time and whenever it does an index rebuild operation. Now, the default fill factor setting is 100%. So SQL Server will fill the entire database page. The problem here is that when you go to insert a new row into the table, when that new row goes into the table, SQL Server has to do what's called a page split to make that row fit. Because unless that new row is going to the end of the table, it's got to go in the middle somewhere. So it's got to split the page, basically take half the data off that page and put it somewhere else so that new row can fit into the middle of that index. So this happens on regular clustered indexes, which are your base table, or on your non-clustered indexes as well. It can happen in both cases, and in both cases, all these page splits and this data being spread all over the place is going to severely impact your performance as SQL Server is trying to navigate through these indexes, trying to find the data that it needs to find. So we want to minimize that by rebuilding the indexes on a regular basis and using some sort of fill factor setting when we build the index or when we rebuild the index to resolve this fragmentation problem. Now, the fill factor setting that you need to use to go along with these rebuild operations is going to be dependent on the kind of data you have, how much data change you have, and how much fragmentation is acceptable before performance starts being impacted on your system. Typically, you're going to use a number somewhere around 70 to 80%. Now, if you've built a table using GUIDs as your primary key, developers, I'm talking to you, then this number is going to get reduced dramatically. The reason for this is because GUIDs are randomly generated. So they get spread out all over the spectrum. So as we're inserting new rows into a table that's got GUIDs as the primary key, the data is going to page split all over the place as these pages fill and get split and fill and get split over and over and over again. This creates an awful mess within the index. This is why, if you work in a shop that's got database administrators, they're going to beat on you and drive into you that you need to be using some sort of numeric value as your primary key within your tables. An identity value, if you're in SQL Server 2008 or below. If you're in SQL Server 2012, either an identity value or a sequence can be used, either one. The net result's going to be the same. Your next question may be, what about this new function called new sequential ID, or new sequential GUID, that's available within SQL Server 2008, I believe? And what this does is every time you run it, it generates a new GUID, but they're in order. So this should fix our fragmentation problem, right? One would assume. The problem that comes up with the new sequential GUID is when we restart the SQL Server, the algorithm that's used resets to a higher number. So we're generating GUIDs, we're generating GUIDs. We restart SQL Server. We now jump way over here to the left, and we start generating GUIDs this way. So the algorithm resets, and everything works fine until we do that first restart. and then we shoot to the far left of the table values, and we start filling up from that side. So now all of a sudden we're causing this whole page splitting problem all over again. So while that does fix some potential problems, it's not all that great, and numbers are still going to be your better option. Now, along with index rebuilding and index defragmentation, we have updating of statistics. Honestly, this fixes a lot of performance problems for a lot of my clients. What these statistics are is just basic numbers in the database, or it's kind of a subtable in the database where SQL Server keeps track of what kinds of data is in the database and how many rows fit within these various ranges. So I've got a slide later on where I'll talk a little bit more about statistics, and we'll look at the statistics in the database to try to dig it out a little bit. Now, when you're doing your database maintenance, if you're doing index rebuilds, you don't need to run update statistics manually. When you do an index rebuild, that will automatically update the statistics for you. So there's no point in running update statistics after the fact. If you're doing an index defrag operation, that does not update the statistics for you automatically. So if all you're doing is index defrags, then you'll want to update the statistics manually or as part of the job that's running the update statistics command. So the differences between index rebuilds and index defrags. With an index rebuild, this may or may not be an online operation, depending on the version of SQL Server you're using and what edition of SQL Server you're using. So anybody still using SQL Server 2000? Couple of hands. All right, don't be shy. Don't be embarrassed by it. Just because you're using a system that's out of support, that's fine. You might want to upgrade, by the way. So if you're using SQL Server 2000, there is no such thing as an online index operation. All indexes are rebuilt offline. What an offline operation means is that users cannot touch the table while the operation is happening. So if I run an index rebuild and my friend Mark over here needs to insert rows into the table, then he's not going to be able to. He's going to be blocked by the index rebuild operation. If you're using SQL Server 2005 or newer, all the way up through SQL Server 2014, if you're using the Enterprise edition of SQL Server, then you can do online index rebuilds, usually. So there's some caveats here. Up through SQL Server 2012, so 2005 through 2008 R2, if you try to do an index rebuild operation on a table that has blob data in it, text, ntext, image, varchar max, and varchar max, or var binary max, then you're not going to be able to do an online index rebuild. That problem was fixed in SQL Server 2012. So in SQL Server 2012, I can now do online index rebuilds if my index, or my table rather, contains those blob data types. Effectively, what an index rebuild does is it is going to create a new index and then basically just drop the old one and rename it. It's more complex than that under the covers, but that's kind of the basic thing of what's happening. As part of that, it updates the statistics on that index as it's doing the rebuild process. An index defrag operation, on the other hand, is always going to be done online. Doesn't matter what version of SQL Server you have, does not matter what edition of SQL Server you have. It is always going to be an online operation. While the index rebuild simply creates this kind of new index by rereading all the data off the clustered index or off the base table, an index defrag is simply moving row by row and moving rows around to try to get them into the right location and try to get everything straightened out. Where an index rebuild is going to read the entire table and build this new index, an index defrag is only moving the rows that need to be moved. So how you pick between these two, as to which one you want to do, is going to depend on the amount of fragmentation that you have. The typical best practice number that most people start with is if your index fragmentation is 30% or less, do a defrag operation. If it's over 30%, do a rebuild operation. The reason we pick that as our breaking point is because typically when we do an index defrag and it's less than 30% fragmentation, it will be faster than if we just rebuild the index. With a table or an index that's more than 30% fragmented, if we do the rebuild, it's typically going to be faster. Now, you'll notice I've been very careful about using the word typically in all these sentences. That's because it all varies, so your mileage may vary on all of this. It's all going to be a matter of testing in your specific system with your specific data types and what kind of indexes you're using as to which number you should be picking as the breaking point. And this can vary from table to table. So realistically, find the breaking point number that works best and just kind of use it. And have that be the number for that specific database. So I mentioned statistics earlier. So statistics are how the SQL Server figures out how to access the data you're looking for. So when you run a query in SQL Server, select star from employee where last name equals Cherry, SQL Server needs to figure out how to go get that data. It just doesn't magically know where this row is that it wants to go find. It has to go crawl a B tree to figure out where this piece of information is. So to do that, SQL Server looks at the statistics of the data to find out what the best index to use is and what operation it should use when it's trying to read that index. It then uses that information to create the execution plan, which is used to actually go get the information that I'm looking for. Now, the statistics that SQL Server keeps are not totally complete statistics about the data in the table. It does not have a one-to-one row mapping relationship with the data in the table to the data in the statistic. If it did, we would simply just scan the table every single time because there would be no point in having statistics. So what we do have are 200 samples out of the table. No matter how big your table is, there are only 200 values which are sampled. We then track the number of values between the values that we're sampling so that SQL Server can get a decent idea of how much data there is for it to crawl through to find the information you're looking for. Now, obviously, this isn't perfect, but it's good enough to get the information that SQL Server needs to go get the data you're looking for as fast as possible, or what it thinks is as fast as possible. So having these statistics be up to date is incredibly important so that we can get the information that we need. If the statistics are out of date, SQL Server is using bad information to try to figure out where to get what information to return to you. Click, there we go. So here is what a statistic looks like. So you can use the command dbcc show underscore statistics, that's a documented command in books online, to see what the information stored within the statistics is. So when you run this command, by default, you're going to get three row sets or record sets as an output. The first one's just got some metadata about the statistic that we're looking at. The second record set tells you the columns that are within this statistic. These columns are typically going to match to an index, although they don't have to. We can have statistics that are not built on indexes. So if we're writing a query that doesn't have an index and we're just scanning the table, SQL Server will create statistics for those columns so that it can figure out how to scan that information. And then the last record set is going to be the actual data, the histogram of the information that we're looking for. So in the first one there, obviously we can see the name of the statistic. That matches the name of an index. I know this because it says IX in front of it, and because this is out of AdventureWorks. We look at the date the statistic was last updated. So this is when SQL Server either automatically updated the statistic, or I manually or through a job ran the update statistics command to actually get the statistics up to date. We can see how many rows there are in the table. In this case, 121,317. And we can look at how many rows were sampled when creating the statistic. So this is another thing to keep in mind about statistics. On large tables, when SQL Server updates the statistics, it is not looking at all the values in the table when it creates the statistic. It's actually looking at only pieces of the table. So it's sampling the table and then creating this sampling report, or this histogram, to show that information. So in this case, it scanned the entire table. It scanned all 121,000 rows to create the statistic. The cutoff point is somewhere in the 500,000 row range. At that point, it's going to start sampling. The default sampling size is 10%. So it's only going to look at 10% of your table. There's 200 steps. We can see what the density of the values are. We can see the average key length matching up to the length of the key in our biggest number there on the record set. This is not a string statistic, and this is not a filtered statistic. So if you're creating filtered indexes in your database, you have filtered statistics as well. So the second record set there, like I said, just shows you the columns in the statistic and how wide those columns are. The third one there is the important one, because that's the actual histogram. So this is what SQL Server is looking at when it's running the queries that you're executing against it. So you can see that we've got the range high key column. So that is simply the values from the key column of the index. In this case, that would probably be the primary key. And it's picked the ones at random that it wants to put in the statistic. The range rows tells you how many rows there are between that number and the next number. So if I turn on the pen here, so for row 718 here, between 718 and 719, there are 218 rows between those two numbers. So that means that there are because these are all whole numbers, that means there are 219 rows that contain the key value of the value 718. So if I do select star from whatever table this was, where product ID equals 718, I'll get 219 rows back. Select range row, or distinct range rows rather, is how many rows have this exact number in them. And then the average range rows is how many rows have this number in them as the average. So it's two different ways of looking at the data, so SQL Server can again figure out the best way to access this information. So every time you run a query, SQL Server's got to go through this information. So like I said earlier, when this stuff's out of date, SQL Server doesn't know what it's doing. Now, SQL Server does update the statistics automatically, assuming you have the setting turned on that says auto update statistics on your database. If you have that turned off, it's not going to update anything automatically. When you've got it turned on, the algorithm that SQL Server uses to figure out if the statistics should be updated or not is when 20% of these rows have been changed, plus 500, then it's time to update the statistics. And the next time the query is run that returns data out of the table, statistics will be updated automatically. So if we've got a small table with, say, 10,000 rows, when 2,000 rows change, we update the statistics. That's not that big a deal. It's not going to take very long to update 2,000 rows in our table, probably. And even if it does take a while, realistically, the statistics are going to be pretty close anyway, so it's not going to be that big a deal. On the flip side, if we've got, say, 10 billion rows in our table, and we need to update statistics automatically, we have to wait for something like 2 billion rows to be updated, 2,500,000,000 rows to be updated. That's going to take a lot of time to change. So SQL Server the SQL Server product team has actually introduced a trace flag that you can add to SQL Server that changes this algorithm. Instead of being a flat 20% plus 500, and unfortunately I didn't put the trace flag number in my presentation here, it will use a sliding scale starting at 25,000 rows. And it'll lower the percentage requirements that are required to update the statistics automatically until we get down to something like 0.1% or something like that. So we can keep the number of rows that we need to change before updating statistics relatively small as far as the numbers go. So that when we have the 2 billion row table, we only need to update, maybe 100,000 or 200,000 rows, and then we update the statistics automatically. The reason we added this feature got added for us, is actually because of Microsoft's SAP implementation. So obviously Microsoft being a huge multi-billion-dollar company, they run on SAP just like everybody else does. They obviously don't run on Dynamics. So with their SAP implementation, as new data was getting put into the system at the beginning of every calendar year, that new calendar year was not getting put into the statistics. it was actually taking about 9 months for the new calendar year to show up in the statistics. So for the first 9 months of running reports against the SAP system, SQL Server had no idea that the new calendar year existed. So it did not know how to find that data. So all the reports were running huge table scans to try to find this, to try to fix this. So by simply putting this trace flag into the product and turning it on, the SAP system got fixed so that we didn't have to run manual update statistics commands against it anymore, and it would just simply update automatically. You can actually read a lot more about this on the SQL Cat website. They've got a full white paper they wrote on it, on why they did it and how the numbers all changed. So the next thing is data compression. Data compression saves space in a few different places within your database. The reason we like data compression in SQL Server is because it's fairly inexpensive and saves us a decent amount of space. Our storage vendors that are all out on the show floor will happily tell you storage is inexpensive, that disk is cheap. The reality is, disk is only cheap when you're buying huge amounts of it. And then you're a large enterprise, and it's no big deal. As you go through your normal day-to-day working with SQL Server, space is not all that cheap, especially if you need lots of it and you're working for a small company. Data compression can save you a ton of space. It'll save you space on the physical hard drive as well as in memory, and it'll also save you a lot of space in your backups as well. Data compression is an enterprise-only feature, and it was introduced in SQL Server 2008. So if you're using 05 or below, this isn't going to apply to you at all. But if you're using 2008 or up and you have Enterprise Edition, then you can use this as an option. Now, on top of normal data compression within the tables, we also have the option for backup compression as well. Backup compression was introduced again in SQL Server 2008 as an enterprise-only feature, but in SQL Server 2008 R2, this was actually turned into a standard edition feature as well. So if you're running standard edition, you can actually make your backups significantly smaller at very, very minimal CPU cost. So data compression does cost you CPU time. Nothing's free. But typically, our CPUs are fairly underutilized at night when we're doing our actual backups. So turning on backup compression is really a no-brainer. It should really be turned on for basically every system. Data compression within the tables, done either at the row level or at the page level, should be turned on selectively based on how big your tables are, how much space savings you're going to get, and if you've got a little bit of CPU power to burn for accessing that data. Typically, when you turn on data compression for large tables in your system, you're going to see about a 2 to 4, maybe 5% CPU increase on the box that's running SQL Server. So it's not that much. So if you've got some CPU power to burn and you're running low on hard drive space, turning on data compression on your indexes may be a good way to go about saving some space. So I was working with a client, and they had a large table, terabyte-ish, give or take, and we wanted to save some space in their system. So we turned on data compression at the page level for their large table. When we compressed the table, it actually compressed from a terabyte down to about 350 gigs. So we saved 700 gigs of drive space. This means we saved 700 gigs of space on production, as well as 700 gigs of space, give or take, within every one of our full backups that we were taking. So this was a huge, huge space savings and huge dollar savings for them, because it extended the life of their enterprise storage array, which is a big EMC box, for another 9 to 12 months, because we didn't have to buy any more space to host all this information. While data compression within a table, you can choose either row or page. Data compression within your backups is simply an on or off operation. As it's compressing, going through all the data, it's simply going to compress whatever it finds using a standard, fairly low-level compression algorithm. Data corruption is the biggest problem we have to deal with within SQL Server databases. Any SQL Server database you have out there can become corrupt and probably will at some point. We consider that data corruption is not a if it's going to happen, but a when it's going to happen. So we always need to be checking for it. and we always need to be prepared for it. Now, when databases become corrupt, it is almost always a hardware problem. Excluding SQL Server 6.5, which we lovingly call the great mangler of data, 99.999% of data corruption problems are problems with the storage. Local disk, RAID controllers, HBAs, whatever's underneath the SQL Server, that's typically what causes the data corruption. And believe it or not, the storage vendors will actually agree with that statement. There is more code running on your hard drives and your RAID controllers than there is within SQL Server. All that code was written by people. People are fallible. So there is bugs in that code. That's why we get driver updates and BIOS updates for our hard drives, is to fix problems. After the 99.99% of data corruption problems that are storage, half of what's left is bad RAM. So it's still not SQL Server problems. It's bad memory sticks that are causing corruption, and that corruption is then being written to the disk. The other half of whatever's left, that is bugs within SQL Server. Knock on wood, we have not had a storage bug that causes data corruption since SQL Server 2005, I believe. So they're really, really good at squashing these, and they're very, very careful about making any changes to the storage code that is actually writing the data down to the disk. Because corruption can happen at really any time, we need to be checking for corruption regularly. The database settings, or the database properties, have some data corruption properties that you can set. You can either tell the database to do checksum validations or to do what's called torn page detection. Checksum is better, but more expensive. Torn page detection is good enough in most cases where you've got high CPU load on the server already. The difference between these is with torn page detection, SQL Server writes a 1 or a 0 in alternating patterns throughout the page, every 512 bytes. So it just writes a 1, 512 bytes later, writes a 0, and then a 1 and a 0. What the torn page detection is looking for is 2 1s or 2 0s next to each other. If that happens, that means the page was not written correctly, and there's a problem. So SQL Server will throw an error message. With checksum validation, what the SQL Server does is it calculates the checksum of the 8K data page and saves that checksum in the 8K page as it writes it to disk every single time it writes it. Every time it reads the page off the disk, it recalculates the checksum and compares it to the checksum that's been stored on the page. If the checksums are different, the page is corrupt and we can't trust the data. So the torn page detection, it's only looking for those 1s or 0s being flipped, or being next to each other, rather. So that means, depending on what kind of corruption it is, that may not catch everything. Whereas checksum validation will catch every single kind of corruption problem that we have. Now, how do we find these corruption problems once they have happened, if we don't want to wait for our users to query for the rows that are corrupt? We do this by running dbcc checkdb. We want to run dbcc checkdb basically as often as we can afford to. We don't want to run it monthly because that's not very often. Weekly is acceptable. Daily is better. It's all going to depend on how long it takes checkdb to run and how long we can afford and how much I/O we can afford to generate by running checkdb. Checkdb is going to be a very I/O intensive operation because it touches every single page within your database. So if you've got corruption problems, it's going to find it, but it's going to be very expensive for you to actually find those corruption problems. Depending on what kind of corruption you have is going to depend on how you're going to resolve that problem. If the corruption occurs in a non-clustered index, I can rebuild that without restoring anything from the database backups. I can simply run checkdb repair, and it'll simply read the values out of the table and rewrite them to the clustered index. This is going to require a short maintenance window to do because I have to kick the users out of the system to do it. Alternatively, a better option is simply to rebuild the non-clustered index. If my clustered index or my base table has become corrupt, Now I have to restore from backups. So this is where having backups comes in kind of handy. So I can restore that page from the backups, roll my transaction logs forward, and get my page up and running and uncorrupt at that point. So most of our repairs are going to be done through DBCC CheckDB. When you run DBCC CheckDB and it finds corruption, one of the really nice things is that it tells you what repair level it needs to fix the problem. So it's going to tell you if it can fix it offline, or if it's going to fix it online, or if there's going to be data loss. There's a couple of different flags for running DBCC CheckDB. The most important one is the one that says allow data loss. That flag means data is going to be lost. It's not joking. It is the only repair level that allows for data loss. If you run CheckDB with some other repair level, your data will be just fine. If you run it with the allow data loss flag, it is going to delete data out of your table. So you're going to need to either restore that page from disk to get that page back, or you're going to need to restore the database to some other system and find the rows that are now missing and bring them back into the table. So that's going to be a manual operation in either case. It's probably, depending on the size of the database, going to be a lot faster just to restore the corrupt page from the backups and move forward. Corruption is going to happen. Keep this in mind. It's just a matter of how you prepare for it as to whether or not your system is going to survive the data corruption. Now, not all corruption can be fixed. If your system objects, the system tables that hold the metadata about all the tables in your database become corrupt, then you're not going to be able to repair the database. You're not going to be able to do a restore of the page and get that information back up and running. At that point, you're looking at a full database restore and then rolling all the transaction logs forward. So you're looking at a long maintenance window to take the system down. So keep this in mind if you do see data corruption problems in system objects. You are looking at some hefty downtime. Another option in SQL Server that I see set incorrectly and greatly misunderstood is the compatibility levels. So compatibility levels do one thing and one thing only. They tell the SQL Server what language syntax that you want to support within your database. And by language syntax, what that means is what version of the SQL Server language you want to support. So I can set a compatibility level to basically any version of SQL Server. If I'm using SQL Server 2005, for example, I can go all the way back to SQL Server 6.5. Say I'm running my database on SQL Server 2008 R2, and I want to use the merge statement. If I've got my compatibility level set for SQL Server 2000, I'm not going to be able to use the merge syntax because that wasn't supported in the SQL Server 2000 language set. This is all this means. This does not affect the version of SQL Server that you can take your database and attach it to or restore it to. Once I've moved a database to a higher version of SQL Server, no matter what the compatibility level is set to, I can never take that database and move it to an older box. So for example, if I take my production database from a SQL Server 2005 machine, I detach it, and I attach it to a SQL Server 2008 machine, I better be really, really sure that I want it on that 2008 machine. Because at that point, I can never go back to SQL Server 2005. My only option at that point is to restore my databases back to the old server to get the application back up and running under SQL Server 2005. The version of SQL Server that you're running is going to determine what versions of compatibility levels you are able to support. SQL Server 2012 is going to support compatibility levels for SQL Server 2005 and up. SQL Server 2008 R2 and below is going to support compatibility levels going all the way back to SQL Server 6.5. So you've got a lot of options available to you, especially on the older versions. I do not know what compatibility levels SQL Server 2014 is going to support. We probably won't know that until the final version of the product comes out, because this is one of the last things that they tend to change. In the beta process, or the beta cycles for SQL Server 2012, up until the final beta, we supported SQL Server 6.5 compatibility. Between the final beta and the RTM release of SQL Server 2012, they ripped out SQL Server 6.5, 7, and 2000 compatibility from us. So that's probably going to happen again if they're going to make that change again. I know myself and a bunch of other MVPs have implored Microsoft to not remove any other compatibility levels as they're moving things forward. The official SQL Server product team policy is they support 2 versions back, 2 major releases back. So theoretically, SQL Server 2014 would support SQL Server 2014's compatibility level, SQL Server 2012, 2008, and they would remove 2005. Hopefully that's not the case. Indexing. The biggest thing with indexes is that they're used to speed up queries. The typical example with an index is it's kind of like a card catalog in the library. Anybody remember card catalogs in the libraries? Sometimes I have audiences that don't. Typically younger people, like in their 20s. So for those of you who don't remember card catalogs, the card catalog at the library was basically the big computer that you have to look up where books are in paper form. Every book had a card, and it was sorted by a couple of different ways. We had one card catalog sorted by title and one sorted by author. Indexes are very much the same way. We create an index to build a new card catalog sorted on some new specific piece of information. When you're building an index, the index is going to be sorted based on the columns that you've selected to put within that index. Now, the downside to indexing is that it causes duplicate data to be stored on the disk. So we're spending space to save time, time being the most expensive resource that we have within a SQL Server database, especially considering that queries are going to time out at 30 seconds by default within .NET applications. Now, creating indexes when you're first getting started can seem a lot like voodoo, and that's okay. That's normal. It is a little bit of art and it is a little bit of science when you first start looking at the indexes. You'll get the hang of it as you get used to doing them. So there's a few different kinds of indexes that you're going to be able to create in SQL Server. The first one is your clustered index. The clustered index is your base table. When you create a table in SQL Server by default, you create a primary key on that table. I hope. You better all be creating primary keys on your tables. If you're not, come see me later. We'll have a discussion. By default, that primary key is going to be the key for your clustered index. So the table is going to be sorted based on whatever that primary key is. That's why we want that primary key of the table to be an identity or a sequence number. What you're going to be creating most of the time to fix performance problems in applications are going to be your non-clustered indexes. These are additional objects within the table that create the duplicate pieces of data, resorted correctly for specific queries. While the clustered index contains the storage for the actual table, the non-clustered indexes contain query-specific settings. For basically every query within your application, you're probably going to need to build a non-clustered index to go with that. Now, non-clustered indexes can be reused, and this is where you start getting into the more arty piece than the science piece as you try to figure all this out. And it can take some getting used to figure out how to make this all work. The next thing we have are full-text indexes. So full-text indexes are totally different beasts from normal non-clustered indexes. They allow you to do kind of a Bing-style or Google-style search against your data using a natural language search algorithm. So instead of saying select star from table where last name equals Cherry, first name equals Denny, I can simply do select star from my full text index, which would be using some sort of predicate like contains table, Denny near Cherry. And it will find all the rows where Denny is near Cherry within the table. We have spatial indexes, so if you're using geography or geometry data types and you want to be able to do lookups to find out what points are near other points, you're going to be looking at spatial indexes. New option in SQL Server 2012 is the column store index. So this is a non-clustered index by its nature because it's not the base table. So a column store index is going to be a row-level non-B-tree style index. So it's a totally new way of indexing for SQL Server. In SQL Server 2014, this has been enhanced by giving us clustered column store indexes. The biggest difference between the two, other than the fact that it's the base table now being stored as column or data or at the column level, is the fact that a non-clustered column store index is read-only, or a clustered column store index is read-write. So you can actually be able to update the data and continue to use the table. This is going to solve a lot of performance problems for tables that are being aggregated and having lots of math done on them. We have XML indexes that can be created on columns that are storing XML data within the column. What the XML index does is it actually indexes the data within the XML document, as well as the relationship between that data and the metadata that surrounds that value. So you can actually do XPath queries against data in an XML document and find the specific rows you're looking for. This takes a lot of space, but is incredibly fast. You can typically speed queries up by factors of 10 or hundreds by creating XML indexes when they're appropriate. We have a new feature also called semantic search. This goes along with full text indexing. This was also introduced in SQL Server 2012. I honestly don't know too much about it just because I don't use it. But I know it's a new semantic language that's supposed to give you even better results compared to the old full text search engine. So when using an indexer to create an index, we start by looking at a query that we're running. So in this case, I've got a very basic query on the screen. Select first name, comma, last name from employee, where last name equals Cherry. So I'm looking for me. The index I would create to find this information would look something like this. Create index, name of the object, on employee. I specify the key columns that I'm looking for. So these are the columns out of my where clause. So in this case, last name. And I tell it I want to include the first name column. The reason I'm including the first name column on that last line instead of putting it as a key column is because I don't want SQL Server to have to worry about sorting that first name column. Because I'm not using that first name column in my where clause, I don't need to include it as a key column, which means SQL Server would have to sort it. So I throw it as an include, SQL Server can just return it to me. If I don't have it as an include column, if I just do create index ix underscore last name on employee, comma, last name, close paren, or open paren, last name, close paren, and I create that index, when I run my query, SQL Server is going to find the row that it's looking for, which has my last name on it, but it now needs to go get my first name from somewhere. For it to go get my first name, it has to go to the base table, or the clustered index, search through that based on the primary key, which is going to be stored in my non-clustered index by default. It's then going to grab that value and return it to me. So this doesn't sound that bad. When I'm only returning a single row, it's really not. Instead of doing 3 I/O, we do 6 I/O. Not that big a deal. Where this becomes a problem is if I'm returning 1,000 rows. So if I'm returning 1,000 rows from my query, maybe I generate 70 I/O to return those 1,000 rows. But if I don't have the column included as an include column, and I have to go back to my base table, I have to go back to my base table for every one of those 1,000 rows that I'm returning. Typically, crawling through a base table, through the B tree, to go get a single row out of the B tree is going to take me 3 to 4 I/O. So now suddenly, instead of doing 70 I/O, I'm doing 3,070 I/O. That's going to take significantly longer for SQL Server to do, as it's got to go find all that data, potentially do physical I/O, physical I/O being the slowest thing it can possibly do, because we have to wait for spinning disk to spin, and get that information back to us. So that is obviously a performance killer right there. Another option that we have is to create filtered indexes. So this was introduced in SQL Server 2008 and can be very, very handy when you know ahead of time what the where clause of your index is going to look like. So here I've got the exact same query, but I've got where end active equals 1 as a predicate in my where clause. So what I'm looking for here is, again, searching through an employee table within an HR database, but now I'm looking for only the active employees, because that's typically what we're going to be looking for in an HR database anyway, where most of the data in our HR database is probably going to be terminated employees. Think about Microsoft. They've got, 80, 100,000 employees. They've probably either had people quit or get fired over time, they've probably had 500,000 employees over time. So 4/5 of their database is going to be data that we don't want to search through. So why include those employees on our index if we don't need to actually find those records? So what we have is the ability to put a where clause on our index as we're creating it. So here we have the exact same index, but we do where active equals 1. What SQL Server is going to do is it's going to see our query, and it's going to see the and active equals 1 in our query. It's going to take that and it's going to look for indexes that have a filter on them that matches that and that meet the other requirements of our index. So in this case, it would find this new index that's filtered and use this new index automatically. The nice thing here, this index is significantly smaller than the index that I would have created before because I've got that filter on it, so I'm only including my current employees. Now, if I look for an employee and I don't specify where active equals 1, or I specify where active equals 0, for example, now SQL Server is going to have to crawl the entire table. But I'm going to do those queries so infrequently, I'm probably okay with that. So I create this, I run my query, we now generate even less I/O because we've got an even smaller index to crawl through. We could turn on compression on top of it and get through the index even faster and have it be even easier for us to go through. Some things to remember about indexes. First thing, indexes are not free. Every time you add an index, we're slowing down our insert, update, and delete operations. The reason for this is because every time we change a row, add a row, or delete a row, we have to update all of our non-clustered indexes at the same time. So if I've got a column that's got 50 non-clustered indexes on it, and I want to insert one row into the table, I have to do 51 writes to the database. One for the base table, and one for each non-clustered index. This is assuming I'm not doing any page splitting or any other bad things are happening. Because of this, only create indexes where the cost of having the index is worth the performance penalty of creating that index. So you don't want to just randomly be creating indexes on the system that aren't getting used. In fact, any unused indexes, you probably want to remove from the database. Now you can figure out what indexes are and aren't being used by querying the DMVs, the dynamic management views within SQL Server. The one that's going to have this information is sys.dm_db_index_operational_stats. I obviously type that in a lot. That will tell you how many times an index has been used for a seek, how many times it's been used for a scan, how many times it's been used for a lookup, and how many times it's been updated. So the gentleman asks, how often is that reset? So it's reset every time the SQL Server instance is restarted. So if your box is up for 9 months, you'll have 9 months worth of data in there. So if you're looking at this information on a box that's been up and running for a long period of time, you'll want to take a snapshot of that information, just dump it to a table somewhere, and then grab another snapshot maybe a week later and compare the values and see what the numbers look like. So that's going to tell you how often the index is used. If it's never used for a scan, a snapshot, or a scan, a seek, or a lookup, and we're updating it a lot, then you're going to want to potentially remove that index from the system. Yes, sir. So the name of the index again, sys.dm_db_index_operational_stats. If you're in SQL Server 2012, just do select star from sys dot and then type in index, and you'll get about 4 options back in IntelliSense. So you'll be able to figure out the right one pretty quickly based on their names. So I've put together some additional reading for you to do as homework, because I know I cannot cover everything there is to talk about in SQL Server. So at this URL, dcac.co/res/TechEd2013, all lowercase, you will find a whole bunch of other stuff so you can read up on more reading on all the same stuff that I've been talking about over the course of the last 73 minutes, according to the big clock up there. I'll leave that on the screen for just a second because I'm seeing cameras flashing. And the deck will be uploaded to the TechEd Channel 9 website within like a day or two, so you'll be able to grab it from there as well. My contact info, thank you all very much for coming. Don't forget to go down and, that's all Microsoft information. Don't forget to go to Channel 9 and TechEd and the Microsoft Learning and MSDN pages for a bunch more information. Please remember to submit your evals on ComNet. You win one of our great prizes here. Conveniently, you can take a picture of that QR code if you have a QR reader on your laptop or your cell phone rather, and submit an eval right now if you don't want to do it later. So I'll leave that up on the screen. Thank you all very much for coming, spending the last of your evening with me.